Hi, I am Sanjay Patel. In today's lecture, we are going to introduce a concept similar to the concept of set of zeros of a function for a homomorphism. Let us recall what is the meaning of a set of zeros. Suppose if we have a function f from say a to b, okay, and then the set of zeros of the function is denoted by the symbol zf, and it means it is set of all those elements in the domain such that the value of the function is 0. So 0 of function means if there exists some point, say x in the domain such that f of x is equal to 0, then this x is called 0 element or 0 of the function f. And we collect all the zeros and form a set, then it is called set of zeros of f. Set of zeros of the function f. For example, let us take one or two simple examples to understand the set of zeros. The first one, let me take f from say r to r, defined as fx is equal to x square minus 2. Okay, we want to find out at which point this function becomes 0. So that is, we want to answer to this question that fx equal to 0 for which values of x. Now fx equal to 0 means x square minus 2 is equal to 0, and that gives us x square is equal to 2, and therefore x must be plus or minus root 2. Therefore x is equal to plus or minus root 2. Okay, fine. So this root 2 and minus root 2 are the two numbers at which the function is 0. So set of zeros of this function contains only these two numbers, root 2 and minus root 2. Let us take another example. Suppose if I take the function f from r to r, defined as fx is equal to say sin x, this trigonometric function, and we know that this fx is 0, that is the sine function is 0 if and only if the argument x is either say multiple of argument x is a multiple of pi, say it is equal to k pi if not for every k belongs to z, for every k belongs to z, because you know that sine pi is 0, sine 2 pi, sine 3 pi, sine minus pi, sine 0 is 0. So set of zeros of sine function in this case is nothing but the set of numbers of the form k pi where k belongs to z. So this is also known to you, and we want to introduce a similar concept to the concept of set of zeros of a function for a homomorphism of rings. And this set of zeros for homomorphisms is known as the kernel of homomorphism. So let me start by defining the kernel of homomorphism. This is a very important set for homomorphism and in the study of abstract algebra. So let us start with the definition of kernel. Let phi be a homomorphism from one ring R to another ring R dash. So the two rings are maybe different. Let phi from R to R dash be a homomorphism. Okay, it's a homomorphism. Then the kernel of phi, the kernel of the homomorphism phi is denoted by the symbol k phi, and there are other symbols also. You can say it is also denoted by k into bracket phi, or in some book you may find the notation I of phi. So this kernel is denoted by k phi, and it is defined as k phi is equal to set of all those x belongs to the domain at which the function phi is 0. Means set of all x belongs to the ring R such that phi of x is equal to the 0 element of the codomain, that is 0 dash. Okay, so this means 0 of R dash. Okay, just for a reference, it is 0 of R dash. So this is called kernel of homomorphism. First thing you can immediately note is that the kernel is always a non-empty set. And the second thing is the kernel is always a subset of the domain ring, the domain set, because we are collecting all those x in R in the domain ring at which the function phi becomes 0. So the first remark about kernel is always subset of domain ring, that is domain of the homomorphism phi. And second remark is the kernel K phi is always a non-empty set. Is always non-empty. Why? Because we have proved about homomorphism that if phi is a homomorphism from one ring R to another ring R dash, then we always have phi of 0 is equal to 0 dash. We know that phi of 0 is equal to 0 dash. So at this point, the value of the function always becomes 0. And therefore, I can say that 0 always belongs to the kernel. So the kernel is always not equal to empty set. It is always not equal to empty set. Okay. So this is something about the kernel, some basic things. To understand how to find kernel of homomorphism, let me take some examples of finding kernel, and then we'll discuss some properties of kernel of homomorphism in our next lecture. So the first problem, I will take a simple one. Say the first example. Number 1, define a function phi from, let phi be a homomorphism from the ring, say C plus dot set of complex numbers to the ring of matrices with respect to addition and multiplication, where I am not taking a set of all matrices, but where I am taking R is equal to this set of all matrices of the form AB minus BA such that A and B are real numbers. So all matrices which are of the form this is my codomain ring, and the operations plus and dot are addition and multiplication of matrices. The domain ring is the ring of complex numbers with respect to addition and multiplication of complex numbers. So let phi be a function, or rather phi be a homomorphism, defined as phi of A plus IB is equal to the matrix AB minus BA, and this is for every Z, every complex number Z is equal to A plus IB belong to the domain set. Then our aim is to find the kernel of phi. Okay, it is very, very simple. So first of all, we know that kernel of phi is set of all those elements in the domain. So domain is a set of complex numbers. So I will take set of all. Let me first write the definition so that you can understand. Set of all x belongs to the domain ring such that phi of x is equal to 0 dash, where 0 dash is the 0 of the codomain. Now here in our case, the set of complex numbers is R, and this codomain ring R dash is the ring of matrices. So this is set of all those complex numbers z belongs to C such that phi of z is equal to 0 dash. So 0 dash means 0 of the ring of this matrices, this type of matrices. And we know that 0 in this ring, 0 in this ring is the 0 matrix, which is given by 0, 0, 0, 0. Okay, so this is our K phi. Let us find out what are the elements of this set. So we have to determine all those complex numbers z of the form a plus ib such that phi of a plus ib is equal to this 0, 0, 0, 0. Okay, 0 element of the codomain, which is nothing but the 0 matrix. So this is equal to set of all z such that phi of a plus ib. By definition of phi, you know, phi of a plus ib is ab minus ba. So this I can write as ab minus ba, this matrix, the value of this phi of a plus ib, and the right hand side is the fixed matrix 0, 0, 0, 0. And these two matrices are equal if and only if all the corresponding entries are equal. So a equal to 0, b equal to 0, and this also gives a and b 0. So this is nothing but set of all z of the form a plus ib belongs to C such that a equal to 0 and b equal to 0. In other words, this z must be 0 complex numbers. Z is equal to 0 plus 0i. So only possibility is that z is equal to 0, or I can write simply the 0 complex number. So thus, in this case, the kernel is singleton 0. Let us take another very important example of kernel, and that example is very useful. So I am taking the second problem. Say let phi be a homomorphism from z plus dot to say zn, or let me write z phi, a particular case z phi comma plus phi comma dot phi. The ring of residue classes modulo phi be a homomorphism defined as phi of say k, not k, let me use some other number or other symbol. Phi of say m is equal to class of m for every m belong to the domain. Okay, then our aim is to determine what is the kernel of homomorphism phi. Determine the kernel of phi. So this is very, very important. Let us prove. So K phi is set of all x belongs to R such that phi of x is equal to 0 dash. Here R is this ring and the codomain ring R dash is Z phi. Okay, and this 0 dash is a 0 element of the codomain ring Z phi, and we know the 0 element of Z phi is nothing but the class 0. So this is equal to set of all elements in Z, set of all x belongs to Z such that phi of x is equal to 0 means class 0. So this gives us set of all x belongs to Z such that, so remember x is an integer here, for which phi of x, that means equivalence class of x must be equal to the equivalence class of 0, because by definition of phi of m is equal to class m, so phi of x is equal to class x here. And if you still try to find what is the value of x, you have to use the properties of equivalence class. The two class x and class 0 are equal if and only if we know that x is congruent to 0 mod phi. Okay, x is congruent to 0 mod phi, and that means it is set of all integers such that phi divides x minus 0. In other words, it is set of all x belongs to z such that phi divides x means x is a multiple of phi. So I can write this as x is equal to phi times k, where k belongs to z. So x is any multiple of phi, then we can have phi divides x. So this set is nothing but all numbers, or rather all integers of the form phi of phi into k, where k belongs to the set z. Okay. So the notation for this set, it is set of all multiples of phi. More precisely, it contains 0, plus or minus 5, plus or minus 10, and so on. So this set is actually, it is denoted by the symbol, say, phi z. Okay. So what we have proved in this problem is the kernel of phi is phi times this phi z, and another notation for this phi z, as you know, it is the principal ideal generated by this number phi. Here the number is phi. So this is actually the ideal generated by the integer phi. So for this example, the kernel is the ideal generated by phi. And there is nothing special about the number 5 here. Instead of the number 5, you can take any natural number n. Then the kernel of the homomorphism phi from z to zn is always the ideal generated by this number n. So let me write as a very important remark. So just remember, note that if phi is a function from rather a homomorphism from the ring of integers to the ring of residue classes modulo n, zn plus n and dot n, defined as phi of m is equal to class m, then the kernel of this homomorphism k phi is always the set which is an ideal generated by m. Okay, so very, very important. Sorry, it is not m, it is n. I must write n here. Yes, it is an ideal generated by this number. In our case, this was phi, so we are getting k phi is equal to the ideal generated by phi. So very important example. So the next problem is, let R plus dot be a ring with unity, and suppose characteristic of R is equal to some number small m, where m is some positive integer. Okay, then let phi be homomorphism from the ring of integers z plus dot to this given ring R plus dot, be a homomorphism defined as phi of n is equal to n into 1 for every n belongs to Z. We already proved in our previous videos that this is a homomorphism. So our aim is to find the kernel of the homomorphism phi. Find the kernel of phi, or rather Instead of this, let me write in a different way. Then prove that the kernel of phi is nothing but the ideal generated by the number m, which is the characteristic of the ring R. Remember, if R has the characteristic, finite characteristic small m, then for this particular homomorphism, its kernel is always the ideal generated by the number m. Let us prove. It is a very interesting problem. So, here we have to show that these two sets are equal. You know what is kernel of phi? The kernel of phi is set of all those numbers in the domain. So I can take set of all, say t belongs to z such that phi of t is equal to the 0 element of the codomain. Okay. So this is our definition. And we want to prove that these two sets are equal. K phi is equal to the set ideal generated by m. So let me begin with by taking any element in the left hand side set. So let say n belongs to LHS, that is n belongs to K phi. This be any element, be arbitrary. If n belongs to K phi, then by definition of K phi, we have phi of n must be equal to 0 dash, that is 0 element of the codomain ring. But what is phi of n? Phi of n is this function, it is n times 1. So I can write n into 1 is equal to 0 dash. Okay. So what I have proved is for the integer n, we have, because n belongs to K phi means n is integer, we have n into 1 is equal to 0. Okay. N into 1 is equal to 0. But we are given that characteristic of the ring R is equal to small m. If characteristic of R is small m, and if R has unity, I can say that m is the smallest positive integer, m is the smallest positive integer such that m into 1 is equal to 0. M into 1 is equal to 0, but in our ring 0 is 0 dash. So m into 1 is equal to 0 dash. Okay. But we have another integer n for which n into 1 is also 0 dash. And m is the smallest one. So what we can say is from 1 and 2, okay, we must have this m divides the number n. Okay, this can be proved that if characteristic of a ring R is m, and if for some integer n into 1 is 0, then m must divide the number n. Okay, if m divides n, that means n is equal to m into something, say m into t for some integer t belongs to z. So n is a multiple of t, multiple of m. So I can say that this n belongs to the set which is the principal ideal generated by m. Okay. So what I have proved here is this: if n belongs to K phi, I have proved that n belongs to the set ideal generated by small m. So thus K phi is subset of this set, and let us our result number 1. Now to prove the reverse inclusion, let us consider some element from the right hand side. So let us start with something, say n belongs to the set which is ideal generated by m, be arbitrary. This is any given element. If n belongs to this set, then by definition of this set, you know what is it? This m, you know, it is set of all k into m, where k belongs to z here. So this implies I can write n is equal to m into some integer t, okay, for some t belongs to z. Let me remove this is not. So n is equal to m into t. Now, if I find the value of this function phi of n, that is, we'll get phi of, let me write this way, phi of n, that is n into 1 by definition of the function phi. This I can write as by putting the value of n, that is m into t into 1. Remember, m and t are integers and 1 is the unity element of the codomain ring. This I can rewrite as, say, t into m into 1. Okay, and that gives me p into 0 element of the codomain ring, because characteristic of R is equal to m, means we must have m into 1 equal to 0 element. So, and 0 into something, or 0 plus 0 plus 0 t times is 0. Okay, so what I have proved is phi of n is equal to 0 dash, and that means this n belongs to the kernel of phi. So if you take n belongs to this set, the idea generated by m, then n belongs to k phi. So thus, if n belongs to this, then n belongs to k phi, and therefore the set ideal generated by m is subset of the kernel phi, and that is our result number 2. And from 1 and 2, we have k phi is equal to this set. So what we have proved here in this example is, if we have this particular homomorphism phi of n is equal to n into 1 from the ring of integers to the ring R with unity having characteristic small m, then the kernel is always equal to the ideal generated by small m. Remember, the kernel is always a subset of the domain ring. So these are the 3 examples I have taken here. You can also prove as an exercise. In this example, I am just leaving it to you. Just a simple thing. In the above example, in this example number 3, if characteristic of R is 0, that is, R is of infinite characteristic, then prove that the kernel of phi is nothing but singleton 0. Kernel of phi is nothing but singleton 0. That will be an easy exercise for you. It's a similar way you can prove this. Okay. So this way you can find kernel of homomorphism. Let me choose some nice example. Say number 4. Say that phi be a function from say C plus dot to C plus dot defined as phi of, say, A plus IB. Let me write phi of Z here. Phi of Z is equal to Z bar. Okay. Then what is the kernel of phi? That is also very, very simple. We can try, and directly also you can write the kernel of phi is set of all complex numbers in the domain ring such that phi of z is equal to 0 of the codomain ring. But codomain and domain both are same ring, and that is the ring of complex numbers. So what I have to look here is all those complex numbers of the form a plus ib such that phi of a plus ib is equal to the zero complex number, that is 0. Okay, and this is nothing but set of all z is equal to a plus ib belongs to c such that a minus ib is equal to 0. This phi of a plus ib is equal to conjugate of a plus ib, that is a minus ib, and this 0 is 0 plus 0i. So comparing the two numbers, we'll get a equal to 0 and b equal to 0. So we are getting a equal to 0 and b equal to 0 here, and that means this contains only one element, which is the 0 complex number, because a and b both are 0. So kernel of this homomorphism is singleton 0. Okay, that's all about the kernel of homomorphism. In the next lecture, we are going to prove some results related to kernel of homomorphism. Till then, goodbye and thank you.